This is the second in a series of videos about equilibrium calculations. In the first video, we talked about the shift and how the stoichiometry was important to the shift and how we could use that to figure out quantitatively how much of each reactant and product was added or subtracted. And now we're going to put that together into what's called an ICE table to find the equilibrium concentrations after the shift happens. Okay, so continuing on, we're going to use a new tool called the ICE table. It is about to be your new favorite thing for the next 3 weeks of class. So we're going to use this tool, the ICE table, to find the equilibrium concentrations. And remember, when we had our 3 steps, we added a stress, the system shifted in response to it, and then we reached equilibrium. So this is what the concentration looks like after the shift, after the punch back occurs. So I'm going to write the ICE table. It's going to have 3 lines, one for each of these different letters. We'll write it in terms of the variables we've been talking about, and then we'll write it in terms of I, C, and E. So the 3 steps that we've been discussing were the stress on the system pushing down on one side of the balance beam, the shift, what the system does in response to that stress to push it back, and the equilibrium, the final state that system reaches. So those are useful terms, but they don't spell anything nice, so we're going to change them so that they spell something a little bit nicer. So we're going to spell ICE, I-C-E. So the I stands for initial. This row is going to be for the initial concentrations before anything happened. The second line is going to be for the change. That's going to be how the system shifts in response to the stress that affects it. And the last line, of course, is going to be equilibrium, how the system looks at the end. And this is the line that we really care about. We are using this tool to find the equilibrium concentration. And the way we're going to make this table is we're going to write ICE on the left side. Then we're going to write our reaction at the top. Reactants goes to products. And we'll put a line here to divide reactants and products, just like we did up here. And then I'm going to add one more line between C and E. And that's because row E, the equilibrium row, is going to equal row I plus row C. So we're going to take this thing in the I column and we're going to add it to this thing in the C row, and that's going to equal this thing in the equilibrium row. So if we had like an A here and a B, we could add them together and get A plus B for our equilibrium. Or if we had a negative number, let's say we had a C and our shift was a negative number, we would still add the positive and the negative number together to get C minus D in our equilibrium rows. This is important. This is how we're going to use that table. We're going to fill in our initial concentrations and the changes in the concentration, just like we did up here in the shift, and we're going to add the rows together to get an equilibrium row. Okay, we're going to do our first example with the steps of how to do an ICE table. So hang tight because you are going to need to use these steps for the next 3 weeks. All right, how to use an ICE table. So the first thing we do when we use an ICE table is determine the shift direction. The good news, we already talked about how to do this. This is our balance beam problem. This is where we're going to say, what is our K value? And we're going to say, what is our Q value? and we're going to figure out which way the reaction is going to shift. So if the Q value is less than K, we're going to shift to the right. And our other situation is if the Q value is greater than K, we're going to shift to the left. So that thing that we practice doing qualitatively, it doesn't go away. You always need to do it every time you make an ice table. Determine the shift direction. All right, great news. We already know how to do that. Next step is to set up and fill in an ice table. More good news, we have just practiced doing that. So we're going to write ICE, initial change equilibrium, on the side. We're going to write our reaction across the top. So in this case, let's do the reaction A goes to 2B, just to change it up. We'll write a line here between reactants and products, and we'll add a line here to remind us to add I plus C equal E. And then we're going to fill in the numbers that go into this table. So depending on the problem, you'll receive different information that you can fill in when you start, but most of the time you will receive initial concentrations. So this is some new nomenclature here. When we put A inside the brackets, that means concentration of, and we're going to put a little subscript I to mean the initial, because this is the initial row. So most of the time you'll be given an initial concentration for A, and you'll be given an initial concentration for the products. And then we have to figure out what the shift is, how much these concentrations are going to change in response to the stress in the system. So here we're doing the shift to the right side. Shifting to the right means that we subtract reactants and we add products. And the amount that we add depends on those stoichiometric numbers. So this side is going to be 1 times X, and this side is going to be 2 times X, just like we practiced. And then the equilibrium row is just going to be the sum of the two numbers above it. So down here, we're going to have initial concentration of A minus X, and we're going to have initial concentration of B plus 2X. All right, that's not so bad. Let's do one on the shift left side just to make sure you've seen everything that you need to know how to use these. So same reaction, similar looking table. Okay, we're going to start with the same initial concentration of A and some initial concentration of B. And then when we shift to the left, we're going to subtract the product side. We're going to add to the reactant side. And there's a coefficient of 2 on this side, coefficient of 1 on that side. And then we're going to add initial plus change for the equilibrium row. Initial concentration of A plus X, and initial concentration of B minus 2X. So just quickly note what those E lines look like. On this side, the A is the minus side and the B is the plus side. And on this side, the A is the plus and the B is a minus. So depending on which direction your shift goes, changes how you're going to fill in the table. So you always have to remember to find the shift before you start. All right, so far, the only new thing was writing numbers in the table. So now we're going to move on to new thing, which is we're going to solve for our unknown X using our K expression, our equilibrium constant. Okay, so let's remember the formula that we use for K, and it is products over reactants. And the rules are that we include the coefficients as superscripts, and we don't include pure liquids and solids. So for this reaction, if we wanted to write a K equilibrium constant for this, it would be B to the second power because of that coefficient over A to the first. And so what we're going to do is we are going to plug in all the numbers from our equilibrium line into our equilibrium constant. So our concentration of B at equilibrium was B initial plus 2x. That whole thing is squared over A initial plus x. Okay, so that's this number for B, we plugged it in here, and this number for A, we plugged it in here. And then if we wanted to do it for the shift left situation, we would do this value for B. So B initial minus 2x, that whole thing squared, divided by initial concentration at I plus x. So again, your K constant is going to look different depending on what you put in your E line. So everything from the E line is going to get substituted in your K expression. And there's going to be math that is going to happen because this is a quantitative problem. More on that later. And then your final step after you solve for x is to answer the question. So I guess we should add that, solve for x, that's what you're doing. And then you're going to use your value for x to answer the question. Usually it wants to know what one of these values from the E row is, right? The point of an ice table is to find the equilibrium concentrations. So after we do this, we're going to try and answer the question about equilibrium concentrations. Okay, so there are really just 4 steps. It just looks like it's long, and it will take them a lot of paper, but it's not actually that difficult to do once you know how to use this tool. So let's do one quick example that has some easy to work with numbers. So here's an example that we'll need an ice table for. So here's the same reaction, A goes to 2B, and we've been given some initial concentrations for A and B, and we've been given an equilibrium concentration. And this one, the question says, find the equilibrium constant. So if we follow our steps, which you can't see, here we go. Step 1 is to find the shift direction. So finding the shift direction means finding Q, and we do actually have to do math at this point now that we're doing a real problem. So Q is going to be concentration of B initial squared over concentration of A initial to the first. And our numbers told us that initial concentration of B was 0, and initial concentration of A was 1. And 0 over 1 is going to be 0. And in this case, when we're making our balance beam, we don't actually know the value for K because we're trying to find it, but we do know that K is always greater than 0. When we first learned about it, we said K can be very, very large or very, very small, but it cannot be a negative number. It's always going to be greater than 0. So if Q equals 0, the balance beam is always going to look like Q less than K. We're always going to shift to the right. So if you see that there's a 0, you may even be able to do this in your head without doing the calculation. If Q is equal to 0, you're always going to shift to the right. Okay, so step 2, make our ice table. Okay, so we're going to do ice along the side. We're going to do the reaction along the top. And I like to include the phases as well, just to remind myself to look and check whether these are going to be pure solids and liquids. All right, so we're going to fill in the table with what we know from the problem. So we know the 2 initial concentrations. There we go, sorry. The 2 initial concentrations are going to be 1.0 molar and 0 molar. We don't know anything about the change. It didn't mention anything, but it did give us one of the equilibrium concentrations. it said the equilibrium concentration of A was 0.75 molar. So we've got part of it. And so now we can plug in our minus and plus X. So we said the shift is towards the right. So we're going to be losing reactants and adding products. And the coefficient on this side is 1. The coefficient on this side is 2. And then we can fill in the rest of the table by adding down 0 plus 2x is 2x. And this one already has a number in the equilibrium column. So this is a pretty straightforward example where there's not going to be a lot of math involved, because you can see we happen to have all of the numbers. We have 2 out of the 3 numbers, that is, 2 out of the 3 numbers in the A category. So we can actually figure out what that X is, right? So we know that the I row plus the C row should equal the equilibrium row. So 1 minus X equals 0.75. So X is going to equal 0.25 molar. And we can also solve for 2X, because remember, we're always trying to find everything in the equilibrium line. If X equals 0.25, 2X is going to be 0.5. So now we can go back and fill in our table with the rest of the information, because we figured it out. Ice along the left, the reaction along the top, reactants divided from products, I plus C equals E. We fill in our numbers that we knew before, so we knew about the 1, we knew about 0, we knew about 0.75 molar, and now we can fill in the rest of what we know. So we know X is equal to 0.25, so the change is going to be minus 0.25 molar. And the change for B is going to be plus 2 times X, 0.50 molar. And then 2X down here, 0.5. So watch out for this. It's easy to forget to put in the coefficient with the 2 times X. So that's why I like to make the table over here first with the generic variables, and then to fill in the numbers once I'm sure. Okay, so that's step 2. Step 3, we're going to be solving for K. So K is going to be products over reactants. It is going to be B squared over A. We are going to get those numbers from the E row of the table. So our value for B was 0.5, and that's going to be squared. And our value for A is going to be 0.75. And you will have to do actual math here with your calculator, and you should get 0.33 equal to K. And then step 4 is to answer the question. The question wanted to know the equilibrium constant, and we were able to find that. Hopefully this example has illustrated how to use the ICE table, how to add I plus C to equal E, how to plug in numbers, how to figure out the shift, and to answer the question. In the next video, we're going to do some more challenging examples to get you ready for full equilibrium shift solving.